The Boeing 787 was designed around an aggressive use of carbon fiber reinforced polymer, CFRP, to reduce structural weight and fuel burn, leading to the adoption of large one-piece composite fuselage barrels instead of traditional riveted aluminum panels. This approach significantly reduced the number of joints and fasteners, improving structural efficiency, fatigue resistance, and corrosion performance. Automated fiber placement and tape laying technologies enabled precise, repeatable manufacturing of these large shells, but also introduced new challenges in inspection and repair, as composite damage such as internal delamination is not always visible. Overall, the 787 represents a shift toward highly integrated structures where efficiency gains come with higher manufacturing and maintenance sophistication. The Airbus A350 follows a hybrid structural philosophy that combines extensive use of CFRP fuselage panels with strategically placed metallic, mainly titanium, fittings where high loads, heat, or concentrated stresses occur. Rather than relying entirely on one-piece barrels, the A350 uses large composite panels assembled into fuselage sections, allowing flexibility in manufacturing and repair while still achieving major weight savings. Titanium is used at critical interfaces such as landing gear, engine pylons, and door surrounds to handle bearing loads and thermal effects that composites manage less efficiently. This balanced approach allows Air to maximize the benefits of composites while retaining proven metallic solutions where physics and maintainability demand them. The A320 and 737 families are built on a refined semi-monocoque aluminum structural philosophy that emphasizes serviceability, durability, and high-rate production rather than maximum weight reduction. Their fuselages are made from aluminum skin panels reinforced with frames, stringers, and longerons, joined using well-understood fastening methods that support fast assembly and straightforward repairs. Over decades, these designs have evolved incrementally through improved alloys, localized composite parts, and increasing automation, while retaining a structure that airlines and maintenance crews know how to inspect and repair quickly. This makes narrow-body metal airframes ideal for short-haul, high-cycle operations where reliability, turnaround time, and cost control are critical. That brings us to the end of Module 2. In this slide, you will find some of the references used in preparing the content and some additional links and references for further reading. If you would like to deepen your understanding of practical stress analysis applications, explore our dedicated stress analysis course.